So we will talk about the interpretation of the physical meaning of Euler's method first, and then make an example of Euler's method using real numbers. Okay, so the physical interpretation. Interpretation of Euler method. Okay, of Euler's method. For Euler's method, what we have here is yn plus 1 will be equals to yn plus h f xn yn, where u f xn yn is y prime. So that is the Euler's method. The physical interpretation is that we assume the slope y prime equals f xy is constant over interval h. So that is the step size, the normalized step size, and that is also equals to dot x, which is xn plus 1 minus xn. So the next step minus the current step is the step size. Therefore, we have the integral from the n step to the n plus 1 step, n plus 1, sorry, n to n plus 1 dy will be equals to from xn to xn plus 1 fxy dx. So the increment of the y will be equals to the integral of from xn plus 1 when the slope is constant. Then what you get here will be yn plus 1 minus yn. We are trying to see what is the increment of uy function as function of x, which is fxn yn xn plus 1 minus xn. Okay, and this is the physical interpretation. The main point is that when you use Euler's method, you assume the slope is constant in between the interval of the step size from xn to xn plus 1. So that is the point I was trying to deliver. Then how the Euler's method can be used in the computational programs such like MATLAB. So we will talk about its algorithm. So for Euler's method, we will first evaluate the increment of the y, right? So we evaluate the function. We will call it the K1. The K1 will be equals to HF xn yn. So that is the difference between the current step and the next step. Then we will calculate the increment function. Basically, the next step, yn plus 1 will be equals to yn plus k1, right? And the third step will be, we will re-update about our x after you finish this step, this current step. So the increment independent variables, which is our x, which is our x. So xn plus 1 will be equals to xn plus h, which h is the step size. And then we will repeat for all the range of x until it's done. So that is the algorithm. We will evaluate the function k1, which is the difference between the yn plus 1 and yn. So you will calculate the increment function based on this k1. Then you will update your current x, which is xn plus 1 will be equals to the current step xn plus the step size. And you will repeat this whole 1, 2, 3 step until you scan all the range of x. And so for this evaluate function, it's just once a step. So you will evaluate once for this part for each step. And then we will make an example for Euler's method using ODEs. Okay, so for example, we have y prime equals to y, and this is an initial value problem, y0 equals 1. So this is first order linear ODE with IVP, which represent by the initial value problem. And you can do the analytical solutions. You can do it by yourself, which is y equals to e to the x. That is the analytical solutions. Okay, e to the y prime will be equals to itself, so it's an exponential function, e to the x, and when initial value equals to 0, e to the x equals 1. So this is correct analytical solutions. Then how we use Euler's method to solve this first order linear ODEs. Then we use numerical method. Which is Euler. Okay, so what I will do is I will make a table. Make a table here. Will be x, which is your independent variable. The y will be the increment function. Then the dy over dx is your slope. So y prime is the slope, and this slope will be constant in between xn to xn plus 1. Okay, so let's make several points and see if that can solve this IVP. So we have our initial value, x will be equals to 0, right? Then when x equals to 0, we have our initial value, which is y0 equals to 1. Okay, and then we know that y prime equals to y. So the slope is 1 here. And this will be constant in between xn to xn plus 1. Okay, so the second point, this is the first point. The second point, let's make an easy number to calculate. We say the h is equals to 1, probably too big, you know, but it's easy to calculate manually. So basically between un plus 1 to n for the independent variable, the increment is 1. So the next point will be 1. And when the next point equals 1, so when x equals to 1, and we can calculate k1 based on the algorithm, right? Will be h times f x 1 y 1, right? And that will be h, which is 1 here, times f function is the y prime here, y prime, so y prime, and y prime equals to y, so y prime, and y prime equals to 1 here, so it's 1. And you know k1 equals to 1, so yn plus 1 is y2, is what we are trying to get. The y2 will be the y1 plus k1. This is the increment function. And y1 is 1, and the k1 is 1, that will be 2. So here is 2. And when y equals 2, y prime equals to y, so the y prime will be equals to 2. Let's make another increment h equals to 1, then the next point will be 2. So we update the independent variables. You can see that how the algorithm will work in computational by using this kind of simple example using manually solve. Okay, so let's do the next point, which x equals to 2. Then what is our k2? The k2 will be equals to h times fx2 y2, right? And the h is still 1, so we increase the same step size, and then times f2 equals y prime, and that is 2 there, so it's 2. And after you calculate k2, you can get the increment function. Y3 will be y2 plus k2 will be equals to 2 plus 2 equals to 4, right? So y3 will be equals to 4. Then you can get y prime equals 4 here. Then you can do, 3, 4 until you scan the orange you want to scan. And we can use a plot to see how this Euler method compared to the initial, to the analytical solutions. So you have 2D plot, which is x, this is y, and we scan 1, 2, 3. You can do the 3 by yourself, and I already did by myself before, so it's 8, 8, okay. Then we can put this Euler method point into the plot. We have 1, 2, 3. We have 1, 2, 3, 4, 5, 6, 7, 8. Okay. So when y equals to 1, that will be when that is 0, so it's past this point. Okay. So this point 0 equals to 1. The second point is 2, so here. The third point will be 4, will be here. Then the fourth point will be 8. Here. So if you put them together, it looks like this. And what is our real number? Our real number, let's use a different color. The real number, which is y equals to e to the x, and I have my real number. Still the initial will be the same, initial value problem. Then when x equals to 1, the point for the e to the 1 will be 2.78, so nearly 3 here. And then when x equals 2, that will be nearly 7, so here. And when x equals to 3, e to the third, that will be even higher, it's like 20 something, I think. Then this is our real solution, y equals e to the x. So you can see that there are differences here between the Euler's method and the real solutions, and that can be because several reasons. First is our step size is so large, right? So that the when you step size is too large, even though you can scan faster, but it will lead significant accuracy issues. Then later we will talk about how you decide the step size of your problem. Okay. So as a conclusion, that the Euler's method is assume that for each interval between xn to xn plus 1, the slope will be constant. And then you calculate the increment function, you update the independent variables, you solve the Euler's method for the ODEs. Okay.